So now I had this this question, and my question was right here, like how did you calculate the probabilities here? How did you calculate the probabilities here? Is there some formula to determine this? And that right there, even though it comes out as a mess, is everything I just copied right here. And if it doesn't get that, I could take a picture of that and put the picture up. But I think I figured it out. Yes, there's a method for calculating the probabilities in this example. The example involves flipping a fair coin twice and calculating the probability of getting a 0, 1, or 2 heads. The scenario can be modeled using the binomial probability distribution. And so which ones are we going to learn about? Oh, we're going to learn one of the binomial probability distributions coming up. And so identify the random variable x. X represents the number of heads and 2 flips of a fair coin. Possible values of x are 0, 1, or 2. And when flipping a coin twice, each flip has 2 possible outcomes, heads or tails. The total number of outcomes for 2 flips is 2 by 2 or 4. Total number of outcomes for 2 flips is 2, 2, 4, and we have heads, 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 tails, tails, heads, tails, tails. And then we have here, we could have heads 0 times, once, or twice. Yeah, so this is a sample space. And so, we could get tails, 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 and tails in both flips, right? We could get, so for each flip, there are these 4 possible outcomes. And we get a head in all those, but we don't get one there. Count the number of favorable outcomes for each value of x. So no heads, there's 1 outcome. 1 head, there are 2 outcomes. Right? 2 heads, there's 1 outcome. So 1 out of 4 is 0.25, and 2 out of 4 is 1/2 or 0.5. This is 0.25. 1 out of 4, 0.25. This is 2 out of 4, or 0.5, and this is 1 out of 4, or 0.25. Now I get it. Probability of x equals 0 is the number of outcomes with 0 heads divided by the total number of outcomes. So probability x0 is the number of outcomes with 0 heads divided by the total number of outcomes. So the number of outcomes with 0 heads is this one, divided by the total number of outcomes, 4, is 1 over 4, 0.25. So that's all the math we just did. And then the general binomial formula. For a binomial distribution, the probability of getting exactly k successes, e.g. heads, in n independent trials, flips, is given by probability x is equal to k, right? So our x value will be number of successes. Like we want to figure out how many successes, 0, 1, 2. And then we have n, which is what's n? N is the number of trials. Here there are 2, so n is equal to 2. K is the number of successes, so we're going with 2 here. Right? So we have 2 here and 2 here. And then we have P is the probability of success on a single trial. For a fair coin, P is equal to 0.5. Right? So probability of success in a fair trial. And then K again is the number of successes that we're going for, and I think, are we going for 2 here? Where did I get the number 2? Oh, number of trials is 2, right? How many successes do we want? And so if we're going for 2, we put 2 there and put 2 here, and it'd be 0.5 to 2, and then we have 1 minus p, so 1 minus 0.5, and then we have n minus k, or 2 minus 2, which is 0, and anything to the power of 0 is 1. And we can just check that, like anything to the power of 0. And I think I could do this. I could do at, and is it at, and then at I put in, what is Google's, at Gemini, there we go, chat with Gemini. And so I do that, I just choose chat with Gemini, and I say I just do at Gemini, and I'm chatting with Gemini, is anything to the power of 0, 1? Anything to the power of 0 equal to 1? I feel like I have to be more careful at Gemini. It's not smart. Introducing Gemini extensions. Get more done with apps all in one place. Your use of Gemini extensions. Okay. Yes, any non-zero number raised to the power of 0 equals 1. 2 to the power of 0 is 1. 100 to the power of 0 is 1. Negative 5 to the power of 0 is 1. However, 0 to the power of 0 is undefined. All right, thank you. That's kind of funny. All right, so now, right, if we have this 2 minus 2 is 0, all that to the power of 0 is 1, and then p to the power of k, 0.5 to the power of 2. We want 2 successes, so we have 0.5 to the power of 2. 0.5 times 0.5 is 0.25. So for 2 heads, right, x equals 2. We have n is the number of trials, 2. We want 2 successes. We have 0.5 to the power of 2 and 0.5 to the power of 0. That's going to be equal to 1. I guess this is like 2 over 2. Kind of looks like there's a line there. And then we have 0.25. That's 0.5 times 0.5. And then we have 0.5 to the 0, which is 1. It's equal to 0.25. And 0.5 and then 0.25. So this is showing us, right? This is showing us that we could do it intuitively. We did it intuitively right here, where he said, hey, what's our sample space for every possible outcomes, the sample space. So with 2 flips, we could get heads, heads. We could get head, tails. We could get tails, heads. We could get tails, tails. And count the number of favorable outcomes for each value of x. So if we have, 0 heads, that's 1 out of 4, 0.25. We have 1 head, right? That's 0.5. We got, one of those. We got one of these, and then we got one. See, that's confusing me a little bit again. We have heads and tails and heads, right? There are 2 outcomes. So 2 out of 4, I guess, right? The possibility of hitting that twice, getting that twice is 0.5. And then 2 heads and heads, the possibility of getting that is 1 out of 4 with all of our possible outcomes. So those are all the possible outcomes for 2 tosses. Yeah, I guess that makes sense. I'm getting a little tired, I think. So then we could do that just intuitively, but then down here it shows us how to do that with the binomial formula. And so there is doing it with the binomial formula. And this binomial formula, it's just formula. That's it. It's like mathematical formula. It's like the point slope formula in algebra, y equals mx plus b, or the quadratic equation in algebra, a squared plus b squared equals c squared, right? Like, they're formulas. People who spent a lot of time doing mathematics, like, they figured that out and they said, here's the formula, and you go, okay, thanks for the formula, and then you use it, right? But binomial is going to describe, like, bi means bicycle, and nomial, I don't know, what's nomial mean? Like, nomial define, right? If we just define it, nominal, there's nominal, but nomial isn't really, I was thinking kind of numbers, right? So maybe it's close to nominal. But so anyhow, we could say, can you please describe the binomial function? Are there any conditions that must be met to use it so that it is only used in certain situations? Boom. And so now we'll learn about the binomial function just as a little preview. And the binomial function is used to calculate the probability of obtaining a specific number of successes in a fixed number of independent trials, where each trial has exactly 2 possible outcomes. So we're looking to see, hey, how many successes do we get when we do a fixed number of trials, where each trial has exactly 2 possible outcomes, success or failure. And the function is based on the binomial distribution. And so I think binomial, I also think of binary. So binary is 2 possibilities, 0 or 1, and on or off. And you could even have 0 or 1 represent success and failure. And so here binomial is like, hey, it's success or it's failure. And so you want to, what's the probability of obtaining a specific number of successes in a fixed number of trials? So this could help you at Vegas, right? This could help you at Vegas, maybe figure out what your odds are of losing or winning your money. And so here, binomial probability formula is this. And we have that definition again. And conditions for using the binomial function To correctly use the binomial function, certain conditions must be met. You must have a fixed number of trials. The number of trials must be fixed in advance. For example, flipping a coin 10 times would have a fixed n equals 10. Only 2 possible outcomes per trial. Each trial must result in only 2 possible outcomes, typically referred to as success or failure. For example, flipping a coin results in either heads, success, or tails, failure. You could arbitrarily make, one of them success, one of them failure. Constant probability of success. The probability of success must remain constant for each trial. For example, if you are rolling a fair die to get a 6, the probability of rolling a 6 is 1 out of 6 and should stay the same across all trials. Independent trials. The trials must be independent of each other, meaning the outcome of one trial does not affect the outcome of another. For example, when flipping a coin, the result of the first flip does not influence the result of the second flip. So trials, right, must be independent. When to use a binomial function? Binomial function is appropriate in scenarios that meet all the above conditions. Here are some examples of situations where binomial function is typically used. Coin flipping, calculating the probability of getting a certain number of heads in a fixed number of flips. So coin flipping, that's cool. Quality control, determining the probability that a certain number of items in a batch are defective, success, failure, built correctly, not built correctly, right? Survey results, finding the probability that a certain number of respondents in a survey favor a particular option. Example of a binomial function in action. Suppose you flip a fair coin 5 times. What is the probability of getting exactly 3 heads? So n is 5, number of trials, k is 3, number of successes, and p equals 0.5, the probability of success, i.e. getting ahead, if you want to get ahead. And using a binomial formula, you're going to have 5 over 3, and then you're going to have 0.5 cubed, and cubed is the number of successes, 5 is the number of trials, and you're going to have 0.5 to the power of 5 minus 3. And so calculate the binomial coefficient. Binomial coefficient is, here we've got 5 over 3, and that's, so this is what this means here, this notation, the binomial coefficient. And that's 5 to the power, 5 factorial over this over that. And that's like the same as combinations, right? The same formula that we learned in the previous chapter about combinations. And permutations, you would just lose this 3 factorial here. And so here we're saying, hey, how many different combinations are there? And so we're calculating the combinations, and that's 10. So we're going to have 10 times 0.5 to the cube times 0.5 to the square. We're going to have 10, 0.25, 0.25, and 0.3125. Thus, the probability of getting exactly 3 heads in 5 flips of a fair coin is 0.3125, 31.25%. By summary, the binomial function is a powerful tool in probability theory, but it must be applied under the right conditions. A fixed number of independent trials, 2 possible outcomes per trial, and a constant probability of success. So there are certain conditions under which you can use the binomial function, and we saw that in an example. And we also learned that you have to do this coefficient. Like, I'm going to define coefficient, right? Like, what's a coefficient? Numerical constant quantity placed before and multiplying the variable in an algebraic expression. Great, that's exactly what it is, right? It's a numerical thing multiplying by something else. And so here's the binomial coefficient. That's just whatever name. They said, hey, here's the coefficient that goes in front of the binomial formula, so they called it a binomial coefficient. And what is that binomial coefficient in this formula? It's the number of combinations. And so this formula we learned about in chapter 4, and we have the number of combinations, and then we multiply it by that. I mean, we just use the formula. It's literally like y equals mx plus b, or a squared plus b squared equals c squared, or whatever that was. I'm not even sure I'm saying that right. Maybe it was, I'm pretty sure that's right. What is oh, I'm just curious. So we'll do the at, just so I'm somewhere else. Gemini, come on, Gemini. At Gemini, what is the a squared plus b squared equals c squared formula? And can you show it to me what it looks like? We'll see if Gemini, Google's chat is as good as, it's not, but we'll see how good it gets. The formula a squared plus b squared plus c squared is known as the Pythagorean theorem. That's right. And here's what it looks like. That's correct. I remember that. But I wasn't sure until I saw it. So that's the Pythagorean theorem. So that's cool. So just like we got that, or the point slope formula, y equals mx plus b, now we have this binomial, what's it called? Binomial function. And again, right, we could calculate probability in situations where it could apply, right? Where it's like this, we could use this function to calculate probability. And so you just think if you're in a situation where it's where there's two things, and one is like your desired outcome and one is a not desired outcome, and you have a fixed number of trials, and there's like a constant probability of success for each trial, and each trial is independent from the other, they don't influence each other, then you can say, oh, let's use the binomial formula, and that will calculate the probability. And this is an example of having a function, right? We have a function that defines the probability, and so we pass some variable into that function. And so here we're passing variables into this function. The main one here is x, and x in this case is the probability of getting exactly k successes in trials, where x is the number of successes we want to realize. And here, just for nomenclature, right, like the function is px up here, but we're kind of mapping that to the normal syntax in the binomial probability formula. But that's this idea of having a variable, and then once we have a variable, we could use that variable in functions, and those functions could create the probability distribution for our discrete, finite or infinite values that can be realized from an outcome of some experiment. And then when we put in that value, assign it to the variable, the function will calculate, and it will produce our outcome, right? 31.25% is the probability of getting exactly 3 heads and 5 flips. And if you could calculate that, then you could like set up a little street hustling corner where you're flipping coins and having people bet on it, and you could know the exact probabilities. And if you're playing that over enough times with enough people, then you'll know when the house wins and when it doesn't. And this is how casinos work. And this is why casinos look like this. Because they make a ton of money. Because it's like, they're massive. They're these huge things, and they're very profitable because the odds are in their favor, and they just run that machine 24/7, 365, and it just pours money into the system, and enough people walk away with money that it makes others want to come in and try to walk away with money. But overall, most of the money stays. That's kind of cool. There's this great book. I'll tell you about it in the next video.